Well, my dear participants, I was talking about the difference between a centered form of the linear model and non-centered form of the linear model. And we were discussing, see, we were somewhere here, yes. So, here when we fit a non-centered model, it is y is equal to beta naught plus beta 1 x plus e, and the estimator least square estimator of beta naught is y bar minus beta 1 hat into x bar, implies 36 point something minus 36 point something, and beta 1 is equal to 5.06. If we fit center from the model, y is equal to beta naught plus beta 1 into x minus x bar plus error, then the estimator of beta naught is just y bar sample mean and beta 1 remains same. So, see what is the advantage of this. One thing is that the estimator of beta naught is very simple, and that is just you estimate the sample mean, and beta 1 no doubt it requires computation. So, actually if we talk of betas estimated in both, there is a concept of correlation also. The correlation matrix, just I would like to go to the here. Suppose M1 is equal to Lm and volume tilde girth data is equal to trees. So, here it is summary M1, it gives minus 36 point something, but when we make centered form of the girth, and that is nothing but we make use of the transform D1 is equal to transform, and this is, say for example, D1 is equal to trees, and then what we do, we are going to redefine D1 is equal to transform D1, and here we are defining a new variable, and that is girth dot c is equal to girth minus mean girth minus mean of the girth. So, could not find the function transform, there is spelling mistake, transform. Now, D1 contains the transform vector also, head D1. See, here the centered form girth C had been there. Suppose we fit a model that is M2, M1, and then again we are fitting say for example it is M11 is equal to Lm volume model as a function of girth dot C and data is equal to D1. When we put summary of M11, it is summary M11 SU double MARY summary. So here it is 30.17. But see, I would like to first define about correlation matrix. And before that, I would like to define variance-covariance matrix, like where suppose you define a vector x1 is equal to C, say for example 2 comma 5 comma 4 comma 3, define another vector x2, say C 3 comma 5 comma 8 comma 5. So we have defined these two vectors. Now we can make a data frame df1 is equal to data dot frame of x1 comma x2, and this becomes data frame df1. This is the data frame df1. Suppose we want to compute variance covariance matrix of this data frame, so it is where df1, it is variance covariance matrix. And if we want to define a correlation matrix, actually it is core df1. So this is the correlation matrix. But suppose we are already having variance covariance matrix, then how we will convert that into the correlation matrix? The function is COV core. It is a function available with base R. So it is where df1. So now it gives direct correlation matrix which is there. Now we see, if we are taking centered form of the data, what happens? MC, it is VCOV of M1, it becomes this one, variance covariance matrix of M1. And VCOV, I have already explained this VCOV means what. Actually, when we talk of beta hat, I have to go on. When we go and then VCOV of M11, it is like this. But when we convert core COV to core VCOV of M1, it gives this correlation matrix, which is, see here, beta naught and beta 1, they are highly correlated. There is minus 0.97 correlation, which is a very high correlation. Whereas, if we talk of COV2 about M11, when we fit a centered form of model, it gives beta 1, beta naught hat and beta 1, they are almost independent, because in the non-diagonal elements, we are having the value 0. So, there is 0 correlation, and numerically it is treated as more stable, and that is why centered form of model fitting is preferred over non-centered form. There is a package known as BRMS, Bayesian Regression Modeling with Stein, and in that package author always recommends to use centered form of the model. Whenever you get a summary of the results, you will find that although it gives the summary in the form of centered form for computation purposes. So, it is more stable, and it is there. See M1C, we have already done these things. C, then we are getting transform values and VCOV. So, we are getting the result, VCOV. So, here VCOV in the uncentered form is like this, whereas here it is almost independent. Note that estimates are highly correlated in non-centered form, whereas they are not in the centered form. Moreover, beta naught hat is simply y bar, which is the mean of the response vector y. For these reasons, centered form is preferred over non-centered form of model fitting. These ideas can be extended to fit multiple regression model also. Like this is the simple linear regression model, and if we want to fit, here predictor is not only girth, rather height also, and so this is the volume is equal to beta naught plus beta 1 girth plus beta 2 height plus error. Now, the model can be fitted as, see, just M2 LM volume versus girth plus height. See, just I would like to go into the PDF, and there I will explain how a multiple regression model, see, fitting a multiple linear regression model. For trees data, one can fit a multiple linear regression model using LM. The model is volume is equal to beta naught plus beta 1 girth plus height, and see how we are translating into a formula. Here the formula is, the first argument is the formula argument, and we are translating it like this: volume is modeled as, instead of equal to, it is modeled as, and beta naught is not written and epsilon is not written. So, it is the coefficient of beta 1, that is girth, and plus coefficient of height, and that is coefficient of beta 2, that is height. So, height is written. So, this is the formula for this data. Actually, these formulas are based on a paper by Winkelson and Rogers published in Royal Statistical Society Series C, and that formula has been adopted by S plus R as well as some other packages also. So, that is a great contribution towards Michelson and Rogers. So, we will go to see here. If we run these things, we will get the results. We will get the results. Again, this is the model fitting, then print a brief summary of results, then summary, detailed summary of the results, then names, then coef M2, it is beta naught, beta 1 and beta 2, then coefficient of summary M2, it is this. When we write coefficient of summary M2, it gives this summary, the summary of the regression coefficients, estimates their standard error, their t value and their p value. From this output, it is evident that both the regressors girth and height, they are significantly different from 0. And then residuals M2. See, we have extracted only first residual, third residual and 31st residual. Then model matrix, we have defined X is equal to model matrix, and C, we can have 1 into 4th row. Suppose if we print model matrix, it is this. The whole matrix is head capital X. So, it is model matrix. Tail capital X. So, this is a matrix of order 31 by 3. The first column corresponds to beta naught, second column corresponds to beta 1, that is girth, and the third column corresponds to the height, and that is beta 2. Now, we can compute residual SS, and that is nothing but deviance. It is deviance M2, residual SS. This is, and then we can get degree of freedom of residual. So, this is 28. Where from this 28 comes? Actually 31 minus 3, because there are 3 betas, beta naught, beta 1 and beta 2. So, 31 minus 3, that is 28. And then MS resid, it is deviance divided by DF residual. It is, and it is nothing but, MS resid is nothing but, it is SQRT of, it is deviance. And then SQRT of deviance is 3.88. Then summary M2 sigma, it is same as summary M2 sigma hat. And then to get fitted values, I am just reporting first 4 and 31st fitted values. So, here predict, they are same as predict, and then variance covariance matrix of beta naught, beta 1, beta 2. So, here there is, if we can compute correlation matrix, see again beta naught and beta 2, they are highly beta naught and beta 2, they are highly correlated, whereas there is somewhat less correlation between beta naught and beta 1, but there is high correlation. So, if we look into the centered form of the model, it is like this, we will define it like this, and we can fit this. This is nothing but volume is equal to beta naught plus beta 1 into girth minus mean of girth, beta 2 into height minus mean height plus error. So, using R commands, now I have given an exercise, multiple see, using R commands, hint, use use the function transform to get centered form of the girth and height and then fit the centered form of it. Exercise 2, generate a data frame on weight, height and age of the students of BSc 5th semester. Fit this data using weight as response and height and age as regressor. Make your comment on the fitted data. Then model comparison. Check whether multiple regression model is better than the simple linear regression model. So I will go into here. We have already talked about these things. This is the centered form. Model comparison. Check whether multiple linear regression model is better than the simple or not. This model comparison is based on the concept of extra sum of squares. Actually, this concept of extra sum of squares, it is discussed in many texts, and that is nothing but extra sum of square due to fitting the less number of parameters. Our implementation is ANOVA. Let M1 and M2 be two models. M1 is the simple linear regression model. M1 is y is equal to beta naught plus beta 1 x1 plus e. M2 is having two regressors, beta naught plus beta 1 x1 plus beta 2 x2 plus error. It may be noted that residual sum of square for M1 will be more than that of M2, because in M1 we are using additional parameter, so its residual sum of square will be lesser than the M1. For trees data with girth as predictor, M1 is equal to this. When girth and height both are used as predictors, it is M2 is equal to LM volume, girth plus height, data is equal to trees. And we are getting the results. See here, deviance of M1 is 524, whereas deviance of M2 is 421. So there is a big reduction, about 100 reducing just by addition of the DF residual. DF residual M1 is 29 and DF residual M2 is 28. So we make the model comparison by using the function ANOVA, and this is the function ANOVA. ANOVA compares two models which are M1 is inside the M2. So M1 inherits from M2. So here model 1, model 2, and see, this is the degree of freedom of model M1, that is 29, and residual sum of square 524, and for model M2 the residual degree of freedom is 28 and residual sum of square is 421. So the difference of these sum of squares is 102.38 and their F ratio is 6.793, and then the p value is 0.0149. So this p value 0.0149, it's 449 is less than 0.05. So that means this shows that the addition of height significantly improves the model. Hence M2 is better than the model M1. So this is the interpretation. Now exercises: fit the dataset trees using SLR and MLR and compare your results with LM. Fit the same data trees using SLR and MLR as centered form and compare your results with the LM. Model diagnostics: the assumptions behind the theory are normality. Actually, there are certain assumptions regarding linear models. One is the assumption of normality, that is, error is normally distributed with mean 0 and variance sigma square I. Homozygosity, the error variance should be constant, that is variance of epsilon is equal to sigma square I, that is all the diagonal elements will be sigma square and they are same. So, that is known as homogeneity of variance. Additivity of effects, effects should be additive. So, here expected value of x is equal to x beta. There are several graphical procedures to check these assumptions, however, we shall discuss briefly about them. Say M2 is the fitted object. So, plot M2 which is equal to 1:3. So, which is equal to 1:3. So, here it is fitted versus residual, fitted versus residual. So, it shows it is a good fit, fitted versus residual. It shows it is a good fit. And second one is QQ plot, theoretical quantiles and standardized quantiles. So, here they are around a line, they are around a line. So, that means the normality assumption is very good and location scale also is very good. From the above plots, it is evident that there is some scope of improvement, as the first plot residuals are not equally distributed around the horizontal line. Similar observations can be seen in QQ plot as well as standardized residuals. Fitting of linear, quadratic, exponential, log models. So, these things I will talk in my next lecture.